Hello everyone, and welcome back. My name is Mr. Cobalt, and in this video I'm going to go over how to assign formal charges to your resonance structures so that you can figure out which of the three resonance structures, if any of them, are the most important to contribute to the overall structure of the molecule. So sometimes the resonance structures are going to be equal in their importance. Um, but sometimes they're not going to be equal in their importance. So how can you tell whether which of these several different Lewis-Dot structures you have is going to be the most important out of them all? And maybe you might have more than one that is the most important. So I'm going to go over a couple of examples where I'm going to show you how to determine which one is going to be the most important. So for A, I have OCN. There's a negative charge. So you'll notice that I've already written out the possible Lewis-Dot structures for this one. They all have brackets, square brackets with the negative charge on the outside. So this is the Lewis structure for this molecule. And there's three different ones, and you'll notice that they differ by whether or not they have single or triple bond or double bonds, right? So again, carbon is only allowed to have 4 bonds because it's in period 2. So there's no expansion of the octet. So if I move electrons from this oxygen to create a double bond, that would be 5. So then one of these electrons would have to move over to give 2 there. So then you could have a double and a double there. And then what you could happen is if these 2 electrons wanted to move in to create a triple bond there, then the next 2 here would have to move in and then create a single bond. And so there's that fluctuation of the electron, creating single double bonds. Now, I don't mean to suggest that there is no fluctuation. There really is motion of the electrons. But again, it's the resonance structures. This molecule does not, in actuality, have double and triple bonds moving around, and it doesn't switch back and forth between these three. The reality is that whatever this structure is, it's got one structure, and it's some sort of average of these two. That's what we mean by a resonance. Okay, so we want to figure out which of these three is going to be the most important resonance structure for this molecule. And so we got to assign formal charges. Now, one of the quickest ways that you can do this is if you know the bonding patterns, then if your element fits the common bonding pattern, then you would expect that to have a 0 formal charge. If you don't know the bonding patterns, or if you're not sure, you can always calculate the formal charge by formal charge is equal to the number of valence electrons for that element minus the non-bonding pairs. So non-bonding electrons, I'll just say electrons, non-bonding electrons minus 1/2 of the bonding electrons. So 1 for each bond. So that's the equation you could use to find it. Otherwise, you could look at bonding patterns. So here, nitrogen has 3 bonds and 1 lone pair. That fits the bonding pattern. So you'd expect this nitrogen to have 0 formal charge. Carbon has 4 bonds. That fits the common bonding pattern. So there you would expect carbon to have 0 formal charge. Now this one, oxygen, is not fitting the bonding pattern. So the bonding pattern of oxygen is 2 bonds, 2 lone pairs. But this has 1 bond, 3 lone pairs. So if you know the bonding pattern of this, then you would know that this has a -1. The -1 formal charge. Now we can calculate that. So we can calculate that by saying, okay, so the formal charge of this oxygen is that, the valence electrons. Valence electrons is 6 for oxygen because it's in group 6. It's got, we're going to subtract out the non-bonding electrons, which are your lone pairs. So it has 3 lone pairs, so that's 6 total. So we're going to subtract 6 from the 6. And then we're going to subtract out half of the bonding electrons, which means 1 for each bond. There's 1 bond, so we're going to subtract out 1. So you add those together and you get -1, which is what was predicted. So again, you can figure out formal charges if you know what the bonding patterns are. If not, you can always calculate it using this formula. Okay, so this one fits the bonding pattern. We have two bonds, 2 lone pairs, so we would expect this one to be 0 formal charge. The carbon has 2 bonds, 2 bonds, that's 4 bonds. That fits the bonding pattern for carbon, that's 0 formal charge. And this nitrogen does not fit the bonding pattern, so it has 2 bonds and 2 lone pairs. So if you know what the charge of that is based on bonding patterns, you could write it, or if you don't, you can calculate it out. So for this, nitrogen is in group 5, so it's got 5 valence electrons. It's got 2 lone pairs. We're going to subtract out the non-bonding electrons, so it's got 2, so that's 4. We're going to subtract out 4. And then it's got 2 bonds. We're going to subtract 1 electron for each bond, so it's -2, and so we get a -1. So that's going to be a -1 formal charge on the nitrogen. Okay, so next, let's look at this one. So here, carbon has 4 bonds again. That's fits the bonding pattern, so carbon has 0. Here, that definitely doesn't fit the bonding pattern. We have 3 bonds and 1 lone pair. So for oxygen, we would calculate 6 for the valence electrons, -2 for the non-bonding electrons, and then 1 for each bond. So that's 3 -3, and we get a +1. So 6 minus 5 is +1. So it's going to have a +1 on the oxygen, and we get let's see, here, for the nitrogen, we have 5 for the valence electrons because it's in group 5, -6 for the non-bonding electrons, and then -1, which is a total of 7. So this is going to be -2. Okay. So that we've assigned formal charges to our atoms, and so now we can decide which one of these is going to be the most important resonance structure for this molecule. And so first you'll notice that the sum of all of these add to -1. So -1, 0, 0 is -1, 0, 0, -1 is -1. And +1, 0, -2 is -1. Now, we're following the rules of formal charge to determine the best. So the first rule was that less formal charge is better than more formal charge. So if you have more zeros in one than the other, that's going to be a good thing. And if you have fewer formal charges, which is another way of stating it, then that's a good thing. So if I'm looking at the number of non-zero formal charges, I have 1 non-zero here, I have 1 non-zero here, and then I have 2 here. Okay, so that's strike 1 against this one. The other issue is the size of those charges. The size of the formal charge is important as well. So smaller formal charges are better than larger formal charges. So again, if I look at this is a 1, and then this is a 1, -1, -1. But you'll notice I have a -2 here, along with the +1. So the fact that this is larger is also a strike against that one as well. So what about these two? Right? We haven't really separated these two yet. Well, that's where the third rule comes in. So the third rule is that the better structure is the one that has the negative formal charge on the most electronegative atom. So which of these is the most electronegative? Nitrogen, carbon, or oxygen? Oxygen is the most electronegative. So oxygen should have the negative formal charge. So you'll notice here it's got a positive formal charge. That's another strike against this one. So this one is really bad. We don't like that one. That's not going to contribute very much at all to the resonance hybrid, whatever that structure is. So then we're looking here at -1 for the nitrogen, -1 for the oxygen. So the main difference between these guys is that oxygen here has the negative formal charge, which is what you would want. So this is the most important Lewis-Dot structure or resonance structure for this element, or for this molecule or ion. So whatever this is, it's going to be more closely related. It's going to look more like this than the other two. Again, it's an average of these three, but this is going to contribute more to the structure than the other two because of the formal charge. Okay. I hope you enjoyed that. In the next video, I'll go over this one as well.